start? Okay. Hi, everyone. First of all, thank you to Lenka and Florent for organizing this nice conference. And I will talk about studying the dynamics of stochastic gradient descent using dynamical mean field theory. So we have heard many times these days that understanding the dynamics of GD and SGD involves a lot of non-trivial questions. And different approaches have been developed in the literature to study the dynamical evolution of these algorithms. For instance, studying the gradient descent in linear networks using tools from random matrix theory that was started by Hopper in the 90s, and then in developing the recent works of Sachs and Ganguly in deep linear networks. Or in the case of online stochastic gradient descent for two-layer networks, as done by Sad and Solla, and in the recent works by Sebastian. And also, as Marilou mentioned and Mathieu Viard has explained this morning, in the case of this hydrodynamic description of the density of weights in two-layer networks with infinitely wide hidden layer. What we are doing is a bit different. Instead, we want to characterize an intermediate setting between the online and the full batch gradient descent. And indeed, we want to track the dynamics of mini batch gradient descent, where the training samples are reused at the end of each epoch. And we have quite few assumptions on the cost function that in general can be non-convex, and we can deal with nonlinear settings. And the long time goal would be to try to answer to some questions, such as what is the role of the batch size in the generalization performance, where SGD finishes, so which regions of the landscapes are attractive for SGD, and what is the nature of the noise introduced by the finite batch size. So we consider two models that are both a mixture of Gaussians, where the centers of the Gaussians are characterized by these vectors V star in dimension D, and the labels are binary, plus minus 1, and we will consider the high dimensional limit where the number of training data n and the dimension go to infinity, while the ratio alpha is fixed. So we have two cases, a linearly separable case with two clusters, where the labels are estimated by a perceptron with sign activation function. And we have a non-linearly separable case with the three clusters aligned, where the two clusters that are the external ones have one label and the central one has another label. And in this case, we use perceptron with the door activation function to estimate the labels. The weight vector is learned by empirical risk minimization of the training loss on the evaluated on the training set, plus ridge regularization term with strength lambda. And the algorithm is defined as follows. Here there is the discrete time weight update. This is simply gradient descent update, but in order to take into account of the finite batch size, we consider a variable S mu dt that selects which training samples are used in the training mini batch in such a way that at each time step, the average fraction of samples in the mini batch is fraction B of the total training set. And in practice, what happens is that at each time step, the mini batch is drawn independently. So one could simply define a discrete time process on ST, drawing at each time step S with 1 with probability B and 0 otherwise. But since we want to consider the continuous time dynamics of this process, we define a different process for ST, where basically each training sample spends a typical time tau in the batch size, and then it's unselected. And in this way, we can define a continuous limit of these dynamics. And in order to track the dynamics of the algorithm, we use dynamical mean field theory with the path integral technique that maybe Francesco will explain in the next lecture. So in practice, we can track the dynamics in the infinite dimensional limit. We have a bipartite model, and the derivation of the DMFT for this bipartite model was done in the paper of Elisabetta Golitzas, Francesco Giulio Biroli, Francesco Zamponi in 2019 in the case of the random perceptron, so to study the jamming transition in hard spheres. And what we do is that we extend this derivation to include mini batch gradient descent and to include structured instead of random input data. So in practice, I will not discuss the derivation, but we consider the infinite dimensional limit at fixed ratio alpha, fixed batch size, and fixed persistence time. And what we do is dimensional reduction starting from a system of infinitely many variables that are strongly coupled, and going to the dynamics just of few variables at the price of adding memory to the dynamics. So the variables that characterize all the properties of the dynamics are the typical gap that is related to the scalar product of the weight vector with the noise in the data, and the magnetization, that is the overlap between the weight vector and the center of the quotients. So we can derive an effective stochastic process for the typical gap, and a differential equation for the the magnetization M that is deterministic. And all these depend on a set of kernels and auxiliary functions. This process must be solved self-consistently, so one has to generate the process many times and average over it, and then iterate the equations for the kernels until they reach convergence. And once the equations reach convergence, we can use them. We can use the kernels also to compute two-point correlation and response functions that are given by a set of fixed point equations that depends on these kernels. And we also can derive analytic expressions for all the quantities of interest for the learning, that are the average training loss, training accuracy, and the generalization error for the two models. And okay, here I'm showing some comparison with experiments for the two different models at zero regularization, and for different values of the batch size. So first of all, what we observe is that lower batch size produces a slowing down of the dynamics and a shift of the early stopping minimum at higher times. And also it improves the generalization performance at longer times. And we also have a quite good agreement, even if the dimension here it was like 5 that is written, and here was around 500. And what we also observe is that the finite batch size acts as an effective regularization. So from the dynamical equation, we can access the average norm of the weight vector, that is CTT in the inset. And here we show that if we compare the fixed regularization stochastic gradient descent at different values of the batch size, and at fixed batch size and different values of the regularization strength lambda, we observe that in both cases the norm of the weight vector decreases, so decreasing the batch size or increasing regularization. So it looks like the batch size acts as an effective regularization. And okay, also we can compare the persistent SGD algorithm that we have defined with the, let's say, standard SGD algorithm. Indeed, once we discretize the DMFT equations to iterate them, we can use the definition of the variables S mu that select the batch size simply as done in the standard SGD procedure, so drawing the batch size at each time step. And we obtain like an SGD-inspired discretization of the DMFT that still gives a quite good agreement with the simulations. So DMFT is also able to reproduce the behavior of standard SGD. And we see that if we compare it with persistent SGD, as we lower the persistent time that each sample spends in the batch size, as this tau gets smaller, persistent SGD approaches SGD. So we hope that this framework can be used to understand some of the questions that have been posed these days. For instance, this paper was shown by Florent, and it's about SGD getting trapped in bad minima with poor generalization due to adversarial initialization. So we could use this DMFT technique to study different training protocols and see where SGD lands. And also, this was presented by Levent. There are these works studying the statistical properties of the gradient of SGD as function of time. And we could use DMFT to also to study this type of results and the statistical the tail behavior of the stochastic gradient. And finally, we are working on extending this framework to first two-layer neural networks in the case of a committee machine with finite number of hidden units. And also we would like to study more realistic data structures, such as the one that Sebastian presented this morning, where we have data with low-dimensional structure that are embedded in a higher dimensional space, like random features or the hidden manifold model. And thank you.
So while the next speaker is preparing, do we have a question for Francesca or two? Well, if not, we can always come up with the questions later, of course.
Let's see. Sì, sì, sì. Ah, sei pigliato.
Okay. Ah. Okay. Let's try with this. Maybe. Ah, okay. Display. Seriously. Okay.
So the next topic is by Stefano on overparametrization and generalization of some shallow neural networks.
Yeah. Thank you, Lenka. So I'm going to talk about overparametrization, which is a topic that many lecturers already talked about, and it's going to be in some neural network. So we have, so I don't really have to motivate what is general overparametrization, what is interesting. I just show this this plot that is taken from the underlying paper over there, that basically is showing you as you increase n, the number of parameters in a neural network, the overall test loss is decreasing and going down and down. And there is a huge literature about that, and we discussed about this also in the last lecture. So this is the setting. What I really want to do is to study this in some simple model where I can compute all the things, I can understand things in detail, and maybe I can get some more some insight. So the model that I'm considering is phase retrieval, which is something that Antoine introduced yesterday, I think. And phase retrieval is just this. You have an input x, you project onto some vector w star, and then you take the square, and so you observe x and y. And this is giving the data set for your teacher. In my case, I'm considering a second hidden layer neural network as a student. And you can see that here you have a quadratic activation function, which means that if I take a single neuron in the hidden layer, I basically have the same model as the teacher. So this means that in some sense, I'm overparameterized with respect to the teacher, in the sense that the function space that the student can represent is larger than the function space that the teacher can represent. But then we realize that we can do something slightly more complex. So we take also a one hidden layer teacher with a quadratic activation function as well. But it is important that if to stay in the overparametrized regime, m star has to be smaller than m. And just to fix the notation, we have d input dimension. We have n samples with alpha equal to alpha d, with alpha something that is finite. And we have m hidden unit for the student and m star for the teacher. Now we are just going to train using gradient descent, and we are in the overparametrized regime that I motivated before. So, okay, just a few related works on this kind of model. There are people that have studied this overparametrization in this scenario, and they basically have shown that most of the people are the empirical loss. So this is interesting, but it's sort of natural. So as I increase the parameters in my model, I can fit more and more data, and so I can achieve zero training loss. Now, this doesn't tell you whether you learn the rule or you learn the patterns. So what about generalization? This is the question. And okay, there is a related work by harmonic that I don't have time to discuss, but people have worked on this on similar model with similar questions. Now, what I want to focus is okay, but what if I don't overparameterize? And then there is this work that we did with Pierfrancesco Lenca, Florent that is not here, and some and Biroli and Camarotta that are not here at the moment. And basically, we analyzed the situation where we match student and teacher. So we have a phase retrieval student, we have a phase retrieval teacher, and we want to understand when gradient descent is achieving good, is finding the good solution. Now there is a work, I can use this. There is a work by San and co-author in 2018, and they show that you have a trivialization, so your loss becomes trivial, smooth, convex, when alpha is going as logarithm in the input dimension. In this case, is going as is infinity far. Instead, if you do the analysis with other techniques that are related to what Pierfrancesco explained in the last lecture, you can see that in fact, gradient flow, gradient descent is able to find the signal much earlier, and in particular, numerically, you can see that this is occurring at alpha equal to 7. So now the question is, okay, if I overparameterize this network, what can I achieve? And this is what I want to analyze next. I have to skip all the analysis, but this is the final result. So this is a phase diagram where I am giving you the transition above which you can find the signal, provided you have enough samples. So here you have m star, the hidden unit in the teacher. So this is giving the complexity of your teacher. And you have the transition, so the number of samples that you need for different input dimensions. So above the dashed line, in this case, d equal 4 input, you can find the solution. And the same is d equal 8, d equal 16, and infinity. So above the dashed region, you can find the signal. And so we can now compare. Okay, and this is so the horizontal line is what was obtained the work that I mentioned before. So we are extending here with to the overparametrized setting, which was not present in their case. So now let's compare this with the phase diagram with the plot that I was showing you before. Now this means that you have a trivialization of your landscape that is occurring at alpha equal to alpha trivialization is equal to 2. So we pass from the alpha that it was logarithmic in the dimension to something that is finite, and actually we see that gradient descent is achieving such alpha, such bound, and so it means that we have a gradient descent is working starting from here if you overparameterize enough your network. And so this is our first result. Now I want to motivate this, okay, the theorem, I don't have time for it, but I want to motivate this with some numerical evidence. And the first thing that I'm going to do is to analyze the landscape. So I'm using this string method that Levin tried to show, but the video didn't work. So you have a string in your landscape. In this case, I'm connecting the student at initialization with the global minimum in my loss landscape. And I'm letting the string evolve in the landscape, and I'm trying to see whether there are minima and saddles, and I'm climbing up in order to reach the teacher. So according to the minimum. So according to our prediction, the critical number of samples that you need should be 2d minus 1. So here I'm plotting the string on the horizontal line, so the section of the strings, for different input dimensions, 4, 6, and 8. And you can see that for d equal 4, n equal 8 is above the threshold, so we have a loss, a nice loss. Instead, d equal 6 and 8 struggle. Here instead, you see d equal 6 already converge as a nice landscape, and here as well for d equal 8. And so, okay, this is a nice way to check the landscape and to see that our theorem holds. Now, another evidence is just looking at the dynamics. So in this case, what I'm doing is I'm considering m star equal to 4 hidden unit for the teacher, and I'm plotting the dynamics for different value of alpha, so for different size of your training set, with input dimension 4, 6, 8, and 16. And here you can see, so according to our phase diagram, the prediction is that for d equal 4, the first alpha it works, if it is just integer, as in this case, is 3. And in fact, you can see that here the generalization loss is plateauing, and here instead is going down. And the same for d equal 8, the transition should be at 4, and again you can see that at 4 the generalization loss is going down, and same for 16. But in this figure you can also see something that is quite interesting, and it is a different convergence rate in the training loss, in the generalization loss for d equal 4 and compared to d equal 8 and 16. In particular, here you can see a polynomial convergence rate that is going as a square of the time. And here instead you can see that it's something that is going exponentially down. So now we want to understand a bit more this phenomenon, why the dynamics is so different in this case. And to do that, we can move to an analysis in the population loss. And we can see, I don't have time to explain why, but trust me that you can map the dynamics of the teacher and the student in the dynamics of two kind of eigenvalues that try to match. So the teacher is associated to a matrix A star, and the student is associated to a matrix A. the eigenvalues of the teacher, the student will try to evolve and match the eigenvalues of the teacher, and some of the eigenvalues of the teacher will be 0, some others will be 1. They different from 0. The one different from 0 are informative, the other ones are non-informative. As the eigenvalues of the student evolve, they will try to they will specialize. Some of them will match the informative eigenvalues, and some others will match the non-informative eigenvalues. We can characterize the dynamics of those kind of eigenvalues. The blue line is for the informative, the orange line is for the non-informative ones. And on the right, you have generalization loss. You can see that there are 3 phases. At the beginning, all the eigenvalues will behave in the same way, will all decrease. Then at a certain point, the informative eigenvalues will specialize toward the teacher, and this is going to happen exponentially fast. But then the non-informative one will take a logarithm, polynomial time to reach 0. So if we look this as we increase the complexity of the teacher M star, you can see that for simple teacher, it is true that you need very few samples to learn the rule, but it will take time to forget the informative, for the non-informative eigenvalue to reach 0. And this is because you have to somehow forget or neglect part of the function space where your student is living. In fact, the student has lives in a space that is much larger than the space of the teacher, and somehow has to neglect part of the space, the function space. And in fact, you can see this transition between a quadratic convergence rate in the loss to an exponential convergence rate in the loss for a complex teacher. And so just to recap, what I show here is that overparametrization helps, and in this model we can show it explicitly. I can show that we show that we have an improvement from a logarithmic trivialization to something that is finite. And in doing so, we found the formula for the number of samples that you need to learn, and we characterize the dynamics, and we adapt the string method to teacher-student scenario. And thank you. Okay. No, we haven't tried that. In which setting are you thinking of? Just phase retrieval, or because otherwise I don't know how to initialize the neural network with the spectral method. Yeah, in phase retrieval you have there are works from for example ULU where he does that, and okay, it works well. Okay.
But the whole point here is to analyze the random stuff. That's kind of that's kind of the main process. So you're not really like trying to design an efficient algorithm.
No. Also because AMP works so well. Yeah.
Okay. If there are no more questions, then should we put on the line maybe because we could storm the weather.
You want also a microphone? Oh. Was I music?
Yeah, we need to switch the microphone.
Thank you, Lenka. Just 1 second. Okay. So I'm going to talk about our work on the linear potential, both for the perceptron model and the spheres. So I will just recap briefly about the perceptron, then I will talk about linear perceptron, linear spheres, and I will conclude. So, like in our framework, the perceptron is basically made of these weights that we call x that live in n-dimensional space. They are continuous variables that live on an hypersphere in n dimension. Then we have m random patterns that are independently normally distributed. And so we can define these gap variables that are just the scalar product between the pattern and the weights minus a certain margin that we call sigma and we use as control parameter. Then of course we take the thermodynamic limit and there is this alpha controlling the number of constraints. So like the constraint is asking that these gap variables must be positive. And if you have some constraint that is unsat, that is some gap that is negative, you can pay an energy cost. So if we look at the sat-unsat phase diagram, it will look like this. So if we have many constraints to satisfy, we don't manage. At the same manner, if we have too large margin sigma. And so in the sat phase, we would have zero energy and the constraint satisfaction problem that is satisfied. But in the unsat phase, we can put a cost function on the unsat gaps and find the minimum of the cost function. So we can do it simply by putting an harmonic cost function. So if we have negative gap, we pay just quadratic cost. We will get a phase diagram that looks like this. So inside that is blue dotted dashed region. The phase space is glassy, meaning that to do proper calculation, you have to use the replica symmetry breaking scheme. And here there is this line that is very special, that is a critical line that belongs to the jamming universality class. So like to understand what's going on, like imagine I cut the phase diagram in this direction. So I look for a minimum here, and I will get a distribution of gap variables that is just continuous. This is the cumulative distribution. And then as I move towards the critical line, I will see something like this. Of course, the number of unsat gaps diminishes, but I see that at zero energy, my distribution gets peaked at a zero gap value. So what's going on? What is going on is that we are meeting the jamming critical point. That is basically, imagine you want to pack spheres inside a certain volume, then you increase the density. At a certain point, you reach a critical point where you cannot pack any longer. So what you get is a contact network that is made of these red lines. And this contact network has very special properties. Namely, it is isostatic. This is crucial. It means that the number of contacts, that is the number of red lines here, is equal to the number of degrees of freedom. So for n spheres in the dimension would be n times d. And if you go to measure the distribution of gaps, of small gaps, you will see a power law. And the same thing for the forces. You will see a pseudo gap here. And these exponents are highly non-trivial. They are irrational numbers. And all this schema is tied together in a very elegant manner. So what we have done is just to study the perceptron. So like to recap, until now we know that this criticality appears here at this transition line. Now we want to study the perceptron where we put just a linear cost function. So it's very simple. You see that every time your gap is unsat, you pay a linear ramp as an energy cost. And notice that this function is non-differentiable in 0. And this is a key point. So what happens? It happens that if I go in the unsat phase and I try to minimize my energy cost, I get a minimum configuration. And if I plot the cumulative distribution of my gap variables, I would see something like this. Now you see that I'm very far apart from the transition line, but already my distribution is peaked in h equal to 0. So one can say, okay, let's count how many gaps are 0, how many contacts I have in my system. So you can define this isostaticity index, that is just the number of contacts divided by n. And if you go to see the phase diagram, you will get something like this. So imagine to move along this line, and as long as you are in the replica symmetric phase, you will get a number of contacts that is less than the number of degrees of freedom. But at a certain point, you saturate to the number of degrees of freedom, and you stay there. And this thing is deeply related to having the breaking of the replica symmetry, and it turns out that this phase is all critical. But now let's understand why we need to have contacts, that is 0 gaps in our minimum. And the reason is quite simple. It's because if you take the derivative, the gradient of our Hamiltonian, you will get just the sum of the ansat patterns. And you see that this is random sum, it will never be equal to 0. Instead, what your system does, it looks for points where the system gets stabilized, and it does through contact forces, like it happens in the spheres. The contact forces are basically these Lagrange multipliers associated to the 0 gap. So you see that this term doesn't contribute to the energy, but it does contribute to the gradient. And these are able to stabilize the system. And there is very intuitive physical point of view. It's if you have spheres interacting with the linear repulsive potential, if they are in contact and you want to overlap them, what you are doing energetically, you are pushing a ball up the hill. And to do this, you need a force that is at least the slope of the ramp. It means that you have to push at least with force equal to 1. Otherwise, you will stay stuck there. And that is the peak that we see in the distribution. So, like studying a bit more what happens in this critical phase, you will get that here the distribution of gaps, of slack variables that we can call, it's like this. We have the Dirac delta that is the 0 gaps, but we have also 2 power laws near h equal to 0. And when you go to measure these power laws, you will get this slope here that you see it matches very well with the critical exponent of the jamming transition line. And the same thing, it happens for the forces. You see that as long as you are in the replica symmetric phase, that is non-critical, you have contact forces distributed like this yellow line. But as soon as you enter in the critical phase, you have pseudo gaps appearing with a new phenomenology that is pseudo gap near force equal to 1. And again, you go to measure the critical exponent, and you find again the jamming universality. So here I've put this equation just to say that if you want to understand what's going on in the critical phase, you have to solve these full RSB PDEs. And of course, it's quite painful, but there is something interesting here. That is, you can make an educated ansatz for P and M, and plug these ansatz inside your equations. Then you try to solve. You will get a set of equations for the universal part of your distribution. And when you go to see this quantity, that is this function P, in this limit, for temperature going to 0, you will get, you are able to measure the critical exponents. And we are able to show that what's going on in the critical phase is exactly having the same equations that you get in the critical point for jamming of spheres. So a very interesting thing is that this phenomenology survives also in finite dimension. And so we have done the thing for the spheres, that now instead of having the weights of the perceptron, your degrees of freedom are just the coordinates of the centers, and your gaps are basically the pairwise distances between the spheres. And then you can write the same Hamiltonian, basically, that is the linear cost function for the overlapping spheres, plus this term that takes into account the contact forces. And you will get configurations that looks like this. So you see that we have contacts that are basically these red lines, but also overlaps between spheres. And all these things stay equilibrated, but in a critical manner. So here is just a recap of some results. So here it's for two spheres in 2 dimensions. We go much beyond the critical, the jamming transition that is at 84. We overlap. We see that the spheres start overlapping, energies goes up, but the number of contacts stays constant, always equal to the numbers of degrees of freedom. And when we go to measure the exponents, the power laws, we see this very good agreement with the jamming critical exponent, and also for forces, here the pseudo gap match very well the exponent for the forces of at jamming transition line. So to conclude, we have studied this simple model in the perceptron and the sphere. We have found a whole critical phase that is quite rare in statistical mechanics, that has a high, has a universality that is very robust. So it goes from infinite dimension down to dimension equal 2. It's related to the jamming critical class, and we are able to find the scaling theory in mean field limit. And with this, I would like to thank you.